All right, let's get right into it. Welcome, future PV designers and engineers, to this dedicated training explainer. So this is a special one. I'm putting together this training guide directly for you, my students, pulling straight from Part 14, Chapter 2 of our book. Since we already covered the earthing foundations in a previous explainer, today we are focusing exclusively on the sky-down threat. Yep, Lightning Protection Systems, or LPS, for utility-scale solar plants. We're going to keep it easy, going from the absolute basics all the way through to a full engineering design using my exact report steps. Let's dive in. Now we're kicking things off with this absolutely terrifying number because it perfectly represents what we're up against. 200,000. That's the peak destructive energy in amps that a single lightning strike can pack. It's a massive natural electrostatic discharge. Just think about that for a second. When you're out there designing a multi-million-dollar utility-scale PV plant, a 200,000 ampere strike is a literal, existential threat to both your equipment and your personnel. If you don't give that energy a safe, highly deliberate path to the earth, well, it's going to find its own path, and you're not going to like it. So here's our 4-step workflow to conquer this. We'll start with the lightning threat, move into risk assessment, tackle physical protection design, go over surge protection devices, and finish up with some common design pitfalls you absolutely need to avoid. All right, Section 1, the lightning threat. Before we do any math, we really have to understand the enemy. So what actually happens when lightning strikes a completely unprotected PV plant? Well, I can tell you it's a lot more than just a loud bang. It can instantly vaporize highly sensitive inverter electronics, wipe out SCADA systems, and literally ignite fires right there in your cable trace. But here's the really scary part. The danger isn't just at the exact point of impact. Lightning induces massive voltage surges that travel through your cables, destroying equipment way far away from the actual strike. And most crucially, an unprotected plant risks human lives by creating fatal step and touch voltages right on the ground around the strike area. To stop this, we rely on the formidable IEC 62305 standard. What's really great about this is how perfectly it lays out your toolkit into 4 sequential engineering steps. Instead of just kind of guessing, this standard is your ultimate blueprint. Part 1 gives you the general principles. Part 2 is your risk management, literally calculating if you even need an LPS. Part 3 guides the physical design to prevent physical damage. And Part 4 covers the electrical systems, basically how to protect all that sensitive equipment from those nasty induced surges. Okay, moving on to Section 2, which is actually Step 1 of your design process, risk assessment. As a designer, your very first job is to answer this simple question: do we even need an LPS? You should never, ever just guess your risk. And honestly, never assume a site needs full protection just because it's a solar plant. We have to mathematically calculate if the threat level actually justifies the cost and complexity of the system. Believe it or not, a lot of structures don't actually need one, but you have to prove it through a strict formula chain. To figure out your dangerous events per year, which we call ND, you're going to need the lightning ground flash density, or NG. You get this by pulling global meteorological data. We're looking specifically at the number of thunderstorm days at your exact site. Take a look at this worked calculation for our 60 megawatt peak reference plant. You take that flash density and multiply it by the physical collection area of your plant. And boom, you start building your real-world risk profile. Now, here's where it gets really important. You have to compare your calculated total risk to this magic threshold right here, 10 to the power of -5. When you calculate your total risk of human life loss, known as R1, you compare it to this tolerable limit set by the IEC standard. If your calculated R1 is less than or equal to 10 to the -5, great, no mandatory LPS is needed. But if your risk exceeds 0.00001, an LPS is strictly required, no exceptions. Now, your dangerous events formula is heavily dependent on these location factors, or CLs. It's a perfect example of how site context completely dictates your design. Say you've got a PV plant located in a city, totally surrounded by taller buildings. It gets a location factor of 0.25, which massively lowers your risk multiplier. But if you have an isolated solar array sitting out on a flat desert terrain with zero height advantage anywhere around it, your factor is 1.0. You are taking the full, unfiltered statistical probability of a lightning strike. All right, Section 3, physical protection design. If you need it, how do we physically intercept the strike? The standard gives us 3 valid methods to design our air termination system. That's just a fancy term for the physical rods catching the lightning.
You've got the protection angle method, which is solid for simple single buildings. You've got the mesh method, which is fantastic for flat roofs. And then you have the rolling sphere method, perfect for complex geometries. But when we're talking about a massive utility-scale solar plant, one of these methods absolutely reigns supreme as the industry best practice. And that is the rolling sphere method. Imagine this for a second. The standard dictates that for a basic Class 4 lightning protection level, we mathematically take an imaginary sphere with a 60-meter radius and basically roll it entirely over your solar array. Any point on your plant where that imaginary sphere actually touches is a point that's vulnerable to a direct lightning strike, and that means it requires an air terminal, a mast, to be placed right there. In a typical 60-megawatt plant example, this geometry might tell you to place a grid of, say, exactly 169 masts, each 12 meters high, perfectly spaced so that sphere never touches the solar panels themselves. It's like a giant invisible force field you're designing.
Which brings us to Section 4, Surge Protection Devices, because just stopping the physical strike is only half the battle.
See, intercepting the direct physical strike is incredible. But even with those beautiful air terminals doing their job, lightning still induces massive voltage surges in all the cables entering your buildings. So, the solution? Dividing the plant into lightning protection zones, or LPZs. I love this concept. The philosophy here is defense in depth. You essentially divide the plant up and install surge protection devices at literally every single boundary. You are progressively choking out the surge energy, step by step, as it desperately tries to move deeper into the sensitive heart of your system, like your inverters and SCADA panels.
Notice the very clear boundary distinction here. Any equipment sitting outside in the wide-open LPZ0A zone is in the direct strike area. It takes the absolute full brunt of the lightning current, so it absolutely demands a heavy-duty Type 1 SPD. Conversely, equipment sitting in LPZ0B is safely tucked under the physical cone of protection of your air terminals. It won't take a direct strike, right? But it still faces massive induced electromagnetic surges. So for that, you need either a Type 1 or a combination Type 1 plus 2 SPD.
Think of this table as your ultimate SPD cheat sheet. A Type 1 SPD is heavily tested against a massive 10 by 350 microsecond full lightning wave. You slap this guy at your main incoming LV panel. A Type 2 SPD handles the shorter 8 by 20 microsecond induced surges, which is absolutely perfect for the inverter AC output or combiner boxes. And finally, a Type 3 SPD is your last line of defense, sitting right at the equipment terminals. Pro tip, never, ever reverse this order in your designs.
Finally, Section 5, Common Design Pitfalls. Let's wrap up with the easiest ways to fail your system design in the real world.
Pay really close attention here so you don't repeat these field mistakes. Number 1, installing an LPS without doing the risk calculation first. Seriously, don't waste the client's money if R1 doesn't demand it. Number 2, and this is absolutely critical, never bury aluminum conductors underground. Aluminum reacts violently with soil and corrodes so fast. Always use copper below grade. Number 3, putting sharp bends in your down conductors. Doing that creates high impedance, literally choking the path to the earth. Number 4, failing to bond all metallic surfaces at the zone boundaries. That allows really dangerous potential differences to build up. And finally, never ever skip your final 3-point fall of potential acceptance test. I mean, a pristine design on paper means absolutely nothing if you don't measure the actual earth resistance in the field. Which leads me to leave you with this exact quote from our training guide: "A beautiful LPS with poor earthing is useless. Your mathematically perfect rolling spheres, your top-tier Type 1 SPDs, your shiny copper down conductors, they're only as strong as the earth connection beneath them. All that lightning energy has to go somewhere, right? And if that path isn't a measured, low-resistance connection directly to the ground, it's going to find its way through your million-dollar equipment, or much worse, your personnel." So, knowing all this, are you ready to design with absolute confidence on your next utility-scale site? Keep these steps close, trust your calculations, and I'll catch you in the next explainer.